In this session, we'll be demonstrating the necessity of an automatic excitation controller or a synchronous generator. Here we are considering a single machine connected to infinite bus. Field is on manual control and the initial power delivered by the generator is 0.1 per unit. Two different cases of power ramping considered. Case 1 is the power ramping from 0.1 to 0.3 per unit, and case 2 is power ramping from 0.1 to 0.5 per unit. Considering the approximate model of generator, with case 1, the limiting value of voltage at bus comes out as 0.5 per unit, and with case 2, the limiting value of voltage at bus comes out as 0.85 per unit. Here this limiting value of voltage at bus is the minimum voltage to be held by the generator so as to maintain the stability. Ensuring the path to our package and then opening the SMIB-system, which we have already seen how to append. To introduce the power ramping effect, we'll drag the ramp block from the electrical library and then enter proper time values in the T low for ramping down and T up for ramping up. So here we require only ramping up feature. So we are introducing 100 second for T low and 0.5 second for T up. And then for setting the excitation control to manual mode, also the initial power delivered by the generator should be set to 0.1 for our case. And now saving the model. For case 1, we require power to be ramped from 0.1 to 0.3 per unit. So we'll edit a ramp level value, a variable which is in the YForm file. So here it's assigned to 2. The final value of ramp is given by initial value plus 2 into the initial value. So here it is 0.1 plus 2 into 0.1. So it comes out as 0.3. So verifying the correctness of diagram. A no error message appears. Now we can create the data files for the model. So a folder of data file is generated. So selecting it and then initiating the load flow analysis first. Now performing the transient stability analysis. Let's assume time span of 20 seconds. So the results file have been created, message appears. For observing various graphical trajectories, we'll set the result display properties. Then bus plots and then bus magnitude, and for turbo we'll assign the mechanical input and generator will check mark the electrical output. So for case 1, we have ramped our power from 0.1 to 0.3 per unit. So let's observe the results. There we have. So the rotor angle, it is stabilizing to a value. Also, the electrical output also stabilizes to the input of 0.3 since the system is lossless. The bus voltage, it reduces. So case 1 leads to the reduction of bus voltage. Also, checking the excitation control, it is constant. It is pertaining to our initial value of power level. So the voltage at bus, it dips. So for case 2, again modifying the ramp level variable. Now we want it to ramp up to 0.5 per unit. So we'll set ramp level to 4 so that it becomes 0.1 plus 4 times 0.1. It is 0.5 per unit. Again performing the same steps. Selecting our data folders. And then initiating transient stability analysis. So let's increase the simulation time. So for case 2, result files have been created. So let's observe the result again. So opening our model and then hitting the result display. So for case 2, we are ramping our power from 0.1 to 0.5 per unit. So let's observe the trajectories. And the input excitation is set to normal, that is manual mode. There we have. So the electrical power is having some oscillations, which we term as unstable case, like loss of synchronism we refer to as. It is clearly observed by the delta excursions taking place. It is monotonically increasing. Similar effect can be observed in the bus voltage trajectory. So it crosses the limiting value of voltage. So if we have automatic excitation controller, then this voltage can be held and the stability could have been maintained.